For centuries, we pictured the cosmos as a vast, quiet void. We imagined stars and planets as isolated objects drifting through absolute nothingness. This classical perspective created a universe of strict rules and hard lines. Everything was deterministic. A switch was either on or off, a charge was positive or negative, and space was either occupied by matter or completely empty. Modern quantum field theory dismantled that assumption entirely. We now know that the vacuum of space is not empty. It is a highly active, vibrating structure packed with latent energy. Physical instruments can measure this underlying activity. We observe spontaneous vacuum fluctuations and watch virtual particles briefly flash into existence. This proves that what looks like a void is actually a restless, dynamic medium. Recognizing that the vacuum has an architecture forces us to look differently at the objects within it. Physicists are now constantly searching for the continuous, invisible fields that dictate the behavior of the matter we interact with every day. Take plasma, the fourth state of matter. When subjected to electromagnetic forces, clouds of highly energetic charged particles naturally organize themselves into complex architectures. Look closely at the surface of our sun. Ambient magnetic fields shape the plasma into massive twisting filaments, deep vortices, and distinct double layers. What keeps these chaotic, high-energy forces from simply flying apart is resonance. Standing waves of energy lock these turbulent forces into persistent, stable patterns. We map quantum fields, we photograph plasma dynamics, and we measure resonance. Yet modern physics lacks a single, unified mathematical equation to connect these distinct physical behaviors together. The microscopic rules of quantum mechanics refuse to align with the macroscopic structures we see in space. This disconnect creates a massive, ongoing blind spot in our modern understanding of reality. The theory of magnetivity attempts to resolve this disconnect by proposing that reality is built entirely upon a coherent magnetic plasmatic continuum. Instead of relying on classical opposites, like 1 versus 0, this hypothesis relies on a single magnetic quantum wave, a fluid spectrum of probability. This maps cleanly onto quantum computing. A qubit exists as a simultaneous blend of 1 and 0 through superposition. Magnetivity suggests its continuous wave is the actual physical substrate linking these quantum states. If two particles are separated by vast distances, this continuous medium allows them to communicate instantaneously, providing a mechanical explanation for quantum entanglement. If this universal magnetic field exists, it would naturally harmonize sensitive quantum systems. It could suppress environmental noise, stabilize qubits, and reduce computational errors. By viewing quantum behavior through a magnetic plasmatic lens, the random probabilities of subatomic particles organize into a structured, interconnected harmonic system. But a unifying framework must apply everywhere. Scaling upward from subatomic waves, this continuous substrate must govern massive macroscopic structures like planetary orbits and galaxies. Under this theory, elementary particles are no longer treated as tiny, isolated billiard balls. They become stable resonant vortices, whirlpools of energy locked in place within the universal magnetic plasmatic field. This forces a radical reinterpretation of gravity. Magnetivity proposes that gravity is not an independent, fundamental force pulling objects together. Instead, it is an emergent effect of varying densities or coherence gradients within the substrate itself. Even the geometry of spacetime ceases to be a static backdrop. It simply becomes the resulting shape the magnetic field takes when it settles into harmonic equilibrium. By defining mass and gravity as large-scale harmonic patterns rather than distinct forces, the theory cleanly connects the predictable movement of planets with the probabilistic behavior of quantum particles. There is an undeniable conceptual elegance to this holistic organizing principle. It echoes respected ideas in modern physics, such as superfluid vacuum theory, which also treats space as an active, dynamic medium. This harmonic perspective shares DNA with a long history of scientific ambition. Physicists like Albert Einstein spent decades at chalkboards just like this, attempting to merge electromagnetism and gravity into one single framework. Decades earlier, thinkers like Nikola Tesla insisted the universe was governed entirely by vibration and resonance. But while magnetivity draws inspiration from these ideas, it proposes an entirely distinct and, critically, completely unproven physical structure. Firmly, we have to draw a distinct line between mathematical elegance and verified reality. Today, the core tenets of the magnetivity hypothesis are strictly hypothetical. Just because a theory successfully unifies seemingly disparate phenomena on paper does not guarantee the universe actually uses that blueprint in practice. For any hypothesis to cross the threshold into accepted science, it must do more than reinterpret old data. It has to generate novel, testable predictions that standard models completely fail to anticipate. For instance, if gravity is truly an emergent coherence gradient, can this theory mathematically predict measurable modifications to how gravity bends light around massive cosmic structures? This map shows the cosmic microwave background. Can magnetivity predict specific, undetected polarization signatures hidden within the thermal radiation left over from the early universe? On a smaller scale, can controlled laboratory experiments reveal entirely new resonant interactions in plasma that our standard electromagnetic equations simply cannot explain today? Without those unique experimental confirmations, it remains a fascinating conceptual framework. Expanding our understanding of the universe requires the imagination to see entirely new structures, but it demands the rigorous math to actually prove they are there.